We are introducing today Dr. Cong Wang. He's a researcher, he's a doctor, he's just finished his doctoral thesis and been promoted to full doctor at the Royal Institute of Technology in Stockholm. They are running their simulations on some of the most powerful supercomputers available, and they have some really interesting work that Cong Wang is going to share with us today. But before I let him take the word, I'll just give you some formal things. Cong will speak about 45 minutes, and then there'll be time for questions. You can always ask questions in between in the chat. There's a chat function, just click on the chat, and then you can type in your questions, and I, as a moderator, will handle them later on. And if you, by the way, wonder who I am, I'm Peter Hojeback. I'm CEO of Avidicare, and I'm your moderator for today. During the presentation, your videos will be off and your mics will be off in order to consume bandwidth such that we all can hear and see what Cong is presenting to us. Then during the questions and answers, your mics can all be turned on and your videos can be turned on again. So with that, it's a great honor and a great pleasure to introduce to you Dr. Cong Wang and his thesis work, or doctoral thesis, ventilation performance in operating rooms, a numerical assessment. Please, Cong, the screen is yours.
Thank you, Peter. Good afternoon, everyone. My name is Cong Wang. Currently, I'm a researcher at the KTH, Royal Institute of Technology. Today is my great pleasure to present, to share some of my research experiences in the area of operating room ventilation with everyone here. And as you see in the screen, today's topic is ventilation performance in operating rooms, a numerical assessment. But before we go to the topic, please let me briefly introduce our research team. So we are the group of fluid and climate technology, and we sit in the Department of Civil and Architectural Engineering. And this department belongs to the School of Architecture and Built Environment, which is one of the 5 schools at KTH. And in terms of research in our group, we mainly focus on 2 aspects. The first one is indoor air quality and health. And we also consider the energy efficiency in buildings. So we aim to achieve a good balance between good indoor climate and energy saving. So here are our personnel in our research group. Currently, we have 4 researchers, and our group is currently led by Dr. Sasang Sadridade. And apart from Sasang and me, we have 2 researchers, Dr. Adnan Polostik and Dr. Cong Wang. And we also receive support and from from 2 affiliated faculties, Professor Emeritus Sudhir Hombali and Associate Professor Dr. Christoph Duwick. So up till now, we have published more than 20 peer-reviewed journal articles in indoor air quality, and especially in this hospital environment. And those journal articles we have published, including both engineering journals and medical journals. This is because we have noticed that there is a huge knowledge gap between the building engineers who build the operating rooms and the doctors or nurses who use the operating rooms. These 2 groups of people, they rarely sit together and listen to each other. Therefore, we feel obliged to share our research experiences with the medical people. Therefore, we publish our research results also in these medical journals. So we aim to bridge the knowledge gap between the engineers and the doctors. Okay, let's get on to the topic, operating room ventilation. And we know that operating rooms are used for performing surgery. And one of the main risks in surgery is the infection. And therefore, this ventilation, operating room ventilation, is very necessary to ensure a good environment to prevent the infection. First of all, let's look at the history of surgery. The history of surgery can date back to the prehistorical times, which is almost as old as the human race. While in these Renaissance times, we have seen significant advances in surgical techniques. However, the surgery remained a treatment of last resort. And this is because human beings need to overcome the three major difficulties. The three major difficulties are bleeding, pain, and infections. So to a large extent, the first two difficulties, bleeding and pain, have been resolved, but the infections remain a major problem. And such infections are referred to as surgical site infections, which is defined as the infections of the incision or organ or space that occur after surgery. So what causes surgical site infections? Surgical site infections are caused by bacteria entering an open incision. And the skin fragments dispersed from the staph are the main source of airborne bacteria that initiate surgical site infections. Approximately 10% of the skin scales carry bacteria, and we refer to them as bacteria carrying particles. In 1980s, the Medical Research Council study, they have studied 8,000 total hip and knee replacement at 19 hospitals. And their study demonstrated an essential linear relationship between the airborne contamination and the infection rate, as you can see in this figure. Then what about the situation in Sweden? Here are some statistics. Surgical site infection is the third most frequently reported group of hospital-acquired infections in Sweden. And it occurred in 7% of surgical procedures in 2006, but in 2011, this number goes up from 7% to 10%. Approximately 1,500 patients die every year, according to the Statistics Bureau of Sweden. And in Sweden, a severe infection can cost 1 million Swedish crown to be treated. So what we can do to prevent surgical site infection? Of course, we can use antibiotics, and we can control the source. By controlling the source, we can either let the surgical staff to wear high-performance clothing to prevent the shedding of bacteria to the surrounding air, or we can reduce the number or activity of the staff in the operating rooms. And then we can also ensure a clean surgical environment, especially by using an effective operating room ventilation. So among these three solutions, we will look at them one by one. Antibiotics. The major problem of antibiotics is the growing antibiotic resistance. So there is a very huge problem with antibiotics. Let's look at some figures. In 1974, about 2% of the bacteria are resistant to antibiotics. And this number goes up to 22% in 1995, and then 64% by 2004. And then when it comes to 2008, this number grows to 70%. So the danger posed by the growing resistance to antibiotics has been described as a global threat, like a ticking time bomb that will explode in the near future. So it has been ranked along with the terrorism. Well, some people believe that the danger posed by the surgical site infections is more severe than the climate change. And people expect that if we don't act now, any major surgery in the next 20 years can kill the patient. Therefore, our reliance on antibiotics must be stopped. As you remember, the second solution is the high-performance clothing. But maybe you have already heard of some news regarding this new Karolinska hospital. The doctors and nurses, they are reluctant to wear very tight surgical clothing because they don't feel comfortable. And we know that to make surgical staff, doctors and nurses to feel comfortable is very important to ensure the safety of the surgery, to eliminate any human errors. Therefore, trying to use very tight surgical clothing is not an option either. So, special efforts and attention should be paid to the third solution, that is, ensuring a clean surgical environment by using effective operating room ventilation. Over the years, many different ventilation strategies have been developed for operating room use, but those ventilation strategies mainly fall into two categories, that is, to main air distribution principles. The first one is turbulent mixing airflow, and the second one is laminar airflow. Turbulent mixing airflow is the most conventional ventilation principle, which relies on the dilution principle. Turbulent streams of the air are supplied to the operating room and mixed with the room air. While mixed airflow is created in the entire operating room. Therefore, when a sufficient amount of air is supplied, the airborne contamination can be diluted. Laminar flow ventilation, on the other hand, is a concept that we have borrowed from these industrial clean rooms. The laminar flow ventilation, instead of relying on dilution principle, it relies on the washing effect. The air is supplied along parallel streamlines at nearly identical speed with a high momentum. This downward airflow aims to directly wash away the particles from the surgical critical zone. Of course, there is some variants of the laminar flow ventilation. One variant is the so-called horizontal laminar flow. In this horizontal laminar flow ventilation, air is supplied from a side wall. And also we have this displacement ventilation. Displacement ventilation relies on this buoyancy effect. Clean, as you can see from the figure, clean chilled air is supplied near the floor level at a low velocity. Because it's cold and it spreads over the floor, when the cold air meets the heat sources, it gets heated, and due to the buoyancy effect, it goes upward. And at the ceiling level, the air is extracted to the outside of the operating room. So at today's webinar is hosted by Care, and we need to introduce this temperature controlled airflow, which has been developed by Care. This novel ventilation principle is really a promising technology. In this temperature controlled airflow ventilation, the air is supplied instead of isothermal air. The air in this temperature controlled airflow ventilation is supplied at two different temperature levels. And we can see here in this figure, we have these central diffusers, we have also surrounding diffusers. And at the central diffusers, 1.5 to 3 degree temperature gradient is established by supplying slightly cold air from the central diffuser. And because of the gravity, the air will be accelerated and it goes downward. So the velocity will be the velocity of the air will reach a maximum speed at the breathing level. Therefore, this downward air will wash away the bacteria carrying particles from the patient and from the sterile instruments. Since we can also see here that the surrounding diffusers will also supply air. Therefore, in the surrounding of the operating room, the airborne contamination will be diluted by the surrounding supply diffusers. So many research works have been conducted in this field, but after reviewing the literature, we still find that there is something unknown. For example, it remains debatable as to the most appropriate ventilation for operating room use. And the applicability of ventilation may vary with working conditions. The ventilation performance are affected by external and internal disruptions. For external disruptions, door opening is one of the most important external disruptions. For internal disruptions, we have surgical lamps, we have surgical staff, and we have surgical equipment. Each ventilation scheme should be thoroughly analyzed, evaluated, and compiled under different working conditions. Therefore, we have summarized 3 research questions, and in our group, we have spent our effort in answering the 3 research questions. Question number 1. So what is the applicability of various operating room ventilation schemes? For instance, we have introduced laminar airflow ventilation, mixing ventilation, and this novel technology, temperature-controlled airflow ventilation. So what are their applicability under different working conditions? This is the question we need to answer. Question number 2. How to quantify and minimize the impact of the opening and the risk of infection? Why we need to investigate this problem is based on the following facts. The airborne contamination in the adjacent corridor can be as high as 180 CFU per cubic meter. And we know that to ensure a clean surgical environment, especially for infection-prone surgeries, we want the airborne contamination to be as low as 10, even lower than 10 CFU per cubic meter. And also, the airflow exchange across the doorway caused by the opening of the door is a very complex mechanism, and it cannot be simply quantified. So we need to look into this phenomenon and propose some kind of solution. Question number 3. How do the internal disruptions affect the performance of various ventilation schemes in operating rooms? We have surgical lamps, surgical staff, and surgical equipment. In terms of the research methods, of course, we can use experimental methods. This is the most conventional and the most scientific based. The figure to the left shows the so-called passive air sampling. So we use the agar plate to collect the bacteria carrying particles. It measures the sedimentation rate of airborne contamination. The figure to the right shows the so-called active air sampling. So there is a pump, and a certain amount of air will be sucked into this sampler, and then this agar plate. We also use the agar plate here, and then the agar plate will be cultivated, and we will count how many bacteria in this amount of air. And in this method, we measure the airborne contamination. But the experimental methods are faced with a number of problems. First of all, the complexity of the operating room airflow makes the experimental investigation very difficult and very expensive. And the experimental methods involve several ethical and logistical issues, so it cannot be frequently repeated. What's more, the experiment needs to include more personnel within the operating rooms during a given surgery. And this will certainly raise the bacterial level. And more importantly, it's not possible to carry out the experiment in the design stage. And therefore, we need to adopt numerical methods. By numerical methods, I mean computational fluid dynamics. So as you can see this figure here, we have plotted this streamline. So by computational fluid dynamics, we of course will obtain the airflow information. But with particle tracking, we can also obtain the distribution, the rich information about the airborne contamination distribution. And also another important feature is that by using numerical methods, we can capture some dynamic or transient features of the airflow and the airborne contamination spread. So in this study, we compared this vertical laminar airflow ventilation and horizontal laminar airflow ventilation. The comparison was made at 4 different airflow rates under 2 different internal constellations. The left figure shows the first internal constellation, and the right figure shows the second internal constellation. And we can compare these two constellations. We see that in the second constellation, we have a person standing between the supply diffuser on the side wall and the operating table. This research work was published in the Journal of Building and Environment. Here are the results. The left figure shows the airflow field, and the right figure shows the airborne contamination level. As you can see here, as the air change rate increases, the airborne contamination steadily decreases. However, as we see here, the marginal effect of increasing the airflow rate is diminishing. At about 40 to 50 air change per hour, the airborne contamination has become quite stable. It won't decrease. If we compare these two internal constellations, that is the horizontal 1, which is the blue curve, and horizontal 2, which is the green curve, we can, well, horizontal 1 is without any obstructions between the supply diffuser and the operating table. Horizontal 2 is in horizontal 2 we have a person standing between. We can see that the presence of this person makes a huge difference. And this huge difference reminds us that we have to inform the doctors and nurses when especially when they use horizontal laminar flow ventilation. Nothing should be present in between the supply diffuser and operating table. In another study, we compared the 3 ventilation schemes: the laminar flow ventilation, mixing ventilation, and temperature-controlled airflow ventilation. We investigated the airflow behavior and the contaminant transport under 3 different ventilation schemes, and I designed an alternative airflow rate. So basically, for the mixing ventilation, the designed airflow rate is 26 air change per hour. For the laminar flow ventilation, the designed airflow rate is 100 air change per hour, and for the temperature-controlled airflow ventilation, the air change rate is 46. And this research was published also in Journal of Building and Environment. Here are the results. So the figure shows the airborne contamination at the operating table in the 3 ventilation systems: laminar flow ventilation, temperature-controlled airflow ventilation, and the mixing ventilation. So of course, we see here laminar airflow ventilation has the lowest level of airborne contamination, and the mixing ventilation is quite high, around 20 CFU per cubic meter. And we know that the standard for auto clean air is 10 CFU per cubic meter. Therefore, this mixing ventilation is not able to fulfill the auto clean air requirements at the design airflow rate. So if we compare the laminar flow ventilation and temperature-controlled airflow ventilation, the difference, of course, laminar flow ventilation is cleaner than temperature-controlled airflow ventilation, but this effect is quite marginal. So the difference is small. But if we recall their airflow rate, laminar flow ventilation uses 100 air change per hour, but temperature-controlled airflow ventilation uses only 46 air change per hour. So it's less than half of the flow rate of laminar flow ventilation. So based on the findings, we can say that temperature-controlled airflow ventilation can serve as an energy-efficient alternative to the laminar flow ventilation. Then we look at the performance at alternative airflow rates. We compare 100 ACH. So in the laminar flow ventilation, we have this 100 ACH, but at the alternative airflow rate, that is 40 or 60 air change per hour, the performance of laminar flow ventilation significantly degraded. But for the temperature-controlled airflow ventilation, it seems more robust at either 40 ACH or 60 ACH. For the mixing ventilation, it shows slightly improvements as the airflow rate increases. The next topic is the opening. The reason why we need to investigate the opening is because it's inevitable for operating rooms to be connected to adjacent spaces through a doorway. And as we have mentioned, the outside operating room, for example, the adjacent corridor is usually more contaminated. If we measure the airborne contamination there, the contamination level can be as high as 180 CFU per cubic meter. And from this video, you can see that the door opening and the corresponding foot traffic can induce a significant amount of airflow change between these two spaces. Therefore, we establish an operating room model and adjacent corridor model. And we equipped this operating room with a sliding door and a hinged door respectively. So the left figure shows the time development of the pressure difference between the operating room and the adjacent corridor. As you can see in this figure, within very quickly, the positive pressure in the operating room is disappeared. Within about less than 3 seconds, the pressure difference is completely gone. And the red figure shows the time development of the airborne contamination. And this is overall airborne contamination. As we can see that as the door opens, there is a sudden increase of airborne contamination level in the operating room. And then after the door is fully closed, the airborne contamination level starts to decay, but it takes nearly 4 minutes for the airborne contamination level to decay to the original level. And this 4 minutes, we usually call it as recovery time. So this is the single door opening. It takes 4 minutes to recover the original contamination level. But then you may wonder, how about multiple door openings? In some type of surgeries, the door opening can be quite frequent, and the frequency of the openings can be quite high. For example, it can be 1 door opening every 2 minutes. And then under the multiple door openings, we can see the airborne contamination level shown in the figure to the right. Because we have this very frequent openings, the operating room ventilation system does not have enough time to recover the original contamination level. Therefore, if we are going to measure the airborne contamination in the operating room, we can get a very high contamination level due to the cumulative effect of frequent door opening. As I said, the airflow across the doorway is a very complex phenomenon, and one of the most important driving force is the temperature difference between the two spaces. Therefore, we have considered 2 different thermal conditions. One is the summer condition, and the other is the winter condition. Here, we assume that because of the high airflow rate in the operating room temperature keeps relatively stable, but the temperature in the corridor can vary with the seasons, with the climate. So in the summer condition, we have the temperature in the corridor about 3 degrees higher than the temperature in the operating room. And in the winter condition, we assume that the temperature in the corridor can be about 3 degrees lower than the temperature in the operating room. And then this figure shows the transient phenomenon caused by the door opening. So at the 0 second, the door is start to be open, but still closed. Nothing would happen. And at the 5th second, the door has already been fully open. We can see that some phenomena had been shown at the 5th second. Then when the time goes to the 15th second, which is 10 seconds after the door is fully open, we can clearly see that the difference between the summer condition and the winter condition. In the summer condition, because the air in the corridor is higher, has a higher temperature than the air in the operating room. The hot air goes up and the cold air goes down, and we see the penetration of the corridor air into the operating room through the upper part of the doorway. But in the winter condition, the penetration of corridor air into the operating room it goes along at the floor level. And the airborne contamination mainly follow the air streams. Therefore, this figure shows the airborne contamination under the two thermal conditions. So under the thermal condition, we can see the bacteria carrying particles. They penetrate into the operating room at the upper level, but in the winter condition, the airborne contaminants penetrate into the operating room at the floor level. Now we look at the overall contamination in the operating room under the two thermal conditions. We can see that under both conditions, both summer and winter conditions, the maximum overall contamination in the operating room is very similar. It's about 2.1, 2.2 increase in the overall contamination. And as time goes by, the contamination level starts to decay, but they decay at a different speed. So we can see in this figure, under the summer condition, the decay is much slower than in the winter condition. And this is because, if we recall this figure, this is because under the winter condition, the contaminants are mainly accumulated at the floor level. And remember that in our operating room ventilation, we usually have this the exhaust vent at the floor level. Therefore, since the airborne contaminants are more closer to the extractor vent, and they will be evacuated more quickly than in the thermal condition, in which the airborne contaminants are accumulated in the upper part of the operating room. So this is the overall contamination in the operating room. But to prevent surgical site infections, we mainly pay more attention to the local contamination that is close to the surgical site, because it's the local contamination that determines the infection rate. So the red figure shows the local contamination at the operating table. If we compare these two figures, we notice that the overall contamination, especially the maximum overall contamination, is very similar between summer and winter conditions. But if we look at the local contamination at the operating table, the contamination level is quite different. In the winter condition, the contamination level can go up to 12 CFU per cubic meter. But for the summer condition, which is indicated by the red curve, we can see here it remains very low. It's no more than 1 CFU per cubic meter. Why it is like this? Why we have overall contamination similar, but we have local contamination significantly different? This is because the interaction between the intruded airborne contaminants and the original ventilation airflow is very complex. And these results tell us that it's not sufficient to focus only on the air volume migration for valid and reliable assessment of infection risks caused by the opening. And I want to mention here is that previous studies, especially engineering studies, they only show the left figure. They only show the overall contamination because they only investigate the overall air volume exchange, but they don't track the airborne contaminants in the operating room. And this study, our study, is one of the first studies that really track the airborne contamination. We pay attention to the spread of intruded airborne contaminants. Then you may wonder, since we have noticed this very important impact of the opening on the airborne contamination, what we can do, how to minimize the impact of the opening. And in our study, we have proposed to reduce the outgoing airflow rate during the operation. We defined 4 cases. Case A is the reference case, And in case B, we reduce the outgoing airflow rate by 10%. And in case C, we reduce it by 20%. In case D, we reduce outgoing airflow rate by 30%. And this, in reality, this can be implemented by either using a variable speed fan, or we can use some dampers at the exhaust vent here. Now we look at the results. The left figure shows the overall contamination, and the right figure shows the local contamination. And we see that as the flow rate reduction goes up from 0% to 30%, both the overall contamination and the local contamination nearly steadily goes down. And a 30% reduction of the outgoing airflow rate can decrease the contamination level to a sufficiently low level. So for overall contamination at 30% reduction rate, the overall contamination is about 0.1 CFU per cubic meter. And for the local contamination, under both summer and winter conditions, it's even less than 0.1 CFU per cubic meter. So this tells us that temporarily reducing the outgoing airflow rate during the operation can be an effective solution to ensure dynamic isolation. And the corresponding research results have published in 2 journals. One is the medical journal, Journal of Infection and Public Health, and the other is the engineering journal, Journal of Indoor and Built Environment. So the third aspect, the third research question is regarding the internal disruptions. And the surgeon posture is one of the most important internal disruptions. Here are 2 figures, the figure to the left and the figure to the right. And we define 2 surgeon postures. As you see here, in the left figure, the surgeon is standing upright, and in the right figure, the surgeon is bending over the operating table. Now we look at the results. Clearly, we can see that the bending posture can block the airflow field from the ceiling diffuser, and this results in accumulation of infectious particles in this surgical area. So this tells us that we need to inform the doctors and nurses when they are performing operations. They should comply with some kind of practices and some kind of rule of thumb, what to do and what not to do. Surgical lamp. Surgical lamp is another important internal disruption. In this study, we compared 2 types of surgical lamp. One is the so-called closed-shape lamp, and the other is the open-shape lamp. We compare the performance of laminar airflow ventilation and the temperature-controlled airflow ventilation. So we first look at the airflow field. For the laminar airflow with the closed-shape lamp, we can identify 2 big vortices underneath the lamp. But with open-shape lamp in laminar airflow ventilation, there is no vortices. The air can pass the lamp and reach the operating table. In the temperature-controlled airflow ventilation, even if with this closed-shape lamp, we can see kind of vortices under the lamp, but this vortices is suppressed significantly. The size is very small, and it does not disturb the far field of the airflow field. And with this open shape lamp in temperature-controlled airflow ventilation, we can see almost no differences compared with without a lamp. So this is the airflow field. Then we compare the contamination at the operating table. With the laminar airflow ventilation, the existence of this closed-shape lamp results in a very high level of contamination, which is more than 100 CFU per meter square per hour. And this is the sedimentation rate of the particles. And for temperature-controlled airflow ventilation, it's no more than 10 CFU per meter square per hour. And with the open shape lamp and in the laminar flow ventilation, it's almost zero contamination. And with open shape lamp in temperature controlled air flow ventilation, the contamination level is also decreased. But overall, we can see that this laminar flow ventilation is rather sensitive to the shape of the surgical lamp. But for the temperature controlled air flow ventilation, it's quite robust in terms of the physical construction, the physical obstruction in the airflow field. Surgical equipment and the impact of surgical equipment mainly lies in the heat load generated or released from the surgical equipment. And in this study, we put as many types of equipment as possible close surrounding the surgical table. And we define 4 cases with different heat load. And the heat load increases from case 1, which is 4.4 kilowatt, to case 4, which is 7.1 kilowatt. So the heat load is gradually increased in the 4 cases. And here we didn't investigate other ventilation schemes. We only investigate temperature controlled airflow ventilation because, as we have said, this temperature controlled airflow ventilation relies on this buoyancy effect. We supply slightly cold air from the central diffuser, and by gravity, the cold air is accelerated. But if I have very high heat load, then this high heat load will generate upward thermal plumes, and these upward thermal plumes will counteract the downward cold air. So it's important for us to look into the performance of temperature controlled airflow with high heat load. So clearly we can see that we defined 4 cases and the results show that these 4 cases fall into 2 categories. The first group or the first category is case 1 and case 2. And then is case 3 and case 4. So for case 1 and case 2, there are some slightly differences between case 1 and case 2. But in both case 1 and case 2, the airborne contamination level is less than 10 CFU per cubic meter. And this fulfills the ultra clean air standard. But for case 1 and case 4, the difference between these 2 cases are small, but together they have very high level of airborne contamination. It's around 20 CFU per cubic meter. So from case 1 to case 2, from case 1 and case 2 to case 3 and case 4, this is a very big change. And why this big change happened? We assume that there must be some fundamental change in the airflow field, and this is the case. So this is the temperature contour plot of the airflow field. So in case 1 and case 2, we can clearly see that the supply air from the central diffuser at the ceiling level can sufficiently reach the operating table and deliver clean air to the surgical site. But in case 3 and case 4, the air from the supply diffuser cannot reach the operating table. And therefore, in case 3 and case 4, this washing effect will be gone. It's not existent anymore. Instead, it's the dilution principle that plays a role in case 3 and case 4. And this dashed line indicates the prediction by the perfect dilution model. We can see that the airborne contamination level in case 3 and in case 4 is close to the prediction by the perfect dilution model. And this further confirms that under very high heat load, this airflow field will not behave as expected. Instead, it behaves more like a mixing airflow ventilation. So we can summarize something from this research. Temperature controlled airflow ventilation can function properly and moderately high heat load and provide good protection. This is case 1 and case 2. So up to 5, slightly higher than 5 kilowatt temperature controlled airflow ventilation can function properly. But when the heat load becomes extremely heavy, it is difficult to establish the desired airflow pattern and achieve the washing effect. And this is what happened in case 3 and case 4. But we need to note that temperature controlled airflow ventilation is still able to work in such a way that it resembles the mixing ventilation and dilutes the airborne contamination. The corresponding research results have been published in one journal article, Journal of Building and Environment, and a number of top conference. AIV, for example, this AIVC, indoor air, and room vent. So based on our research, I think we can give some recommendations for the usage and then design of operating room ventilation systems. First of all, we can say that the clean air is not only a result of high airflow rates. The airflow distribution is of critical importance in reducing the airborne contamination. That's why we need to spend time in finding alternative, more promising ventilation principles. And then the mixing ventilation cannot reliably maintain an ultra-clean environment, and therefore it is generally not recommended for infection-prone surgeries. I think this has become kind of a common sense in nowadays. And then sufficiently airflow rate should be used for laminar airflow ventilation to make sure it functions properly and achieve the desired performance. If we recall the study, we firstly investigated the laminar airflow ventilation at 100 ACH, which is the desired airflow rate. But then when we decreased the airflow rate to 60 or 40 ACH, the laminar airflow ventilation will not fulfill the ultra clean air requirements. And then we can say that if we recall the surgical lamp case, we can say that laminar flow ventilation is sensitive to physical obstructions in the airflow path. And surgical staff should make sure to comply with the operating room protocols to avoid the failure of laminar flow ventilation. And our new technology, temperature controlled airflow ventilation, represents a robust and efficient alternative to laminar flow ventilation. And then when it comes to the opening and for the traffic, we should say that operating room for the traffic should be minimized to reduce the frequency and the duration of the door opening. And that's it for today. Thank you for listening, and I welcome questions.
Thank you very much, Dr. Cong Wang. That was a very good review. I have gotten an overview, over the topic, and it's amazing how much you can do. And at the Vidicare, we are working further together with you now to take these learnings even further and to make sure that we are coming even closer to being able to see the bacteria. So I hope you thought it was all fascinating. And now, please, you're free to open your mics and ask questions or just type them into your chats if that is preferred.